Hey, Calc BC. Today is a big day because today is the day that we start Unit 3. Unit 3 is all about integration. Our lesson is called Integration, Riemann Sum, Indefinite and Definite Integrals, and Use Substitution. This again will be a lesson filled with review from Calc AB, and it comes specifically from Units 6, 7, and 8 of College Board's version of the course. So you can see the red boxes are showing what lessons we specifically are going to be covering today. So we've got the Riemann sum lessons, definite and indefinite integrals, and integration using substitution. That's what we're going to be talking about. The next three lessons, so 3.1, 3.2, and 3.3 in our notes will cover several topics from Units 6 and Units 7 from College Board's course description. Unit 8 is technically AB content, but you didn't cover it last year because of the school closure. So after our first three lessons, then we're going to take several lessons to go through all of these applications of integration that you missed out on last year. Notice the purple lessons say BC only, so we are not going to be covering those at this time. Our Unit 3, which we are starting today again, is going to be only AB content, even though Unit 8 is something that you haven't seen before. So we'll come back and hit these purple lessons after this unit. But yeah, Unit 3 is going to be our last review unit. Then we'll move into BC, brand new content after that. And with that, let me switch over to the notes. All right, so we're going to start off our integration unit with a review of Riemann sum. So let's take a look at this question. A car is traveling so that its speed is never decreasing during a 12-second interval. The speed at various moments in time is listed in the table below. I've already kind of started to construct the graph. So for part A, we're going to sketch a possible graph for this function. I decided to put time on the x-axis and speed on the y-axis. And all I'm going to do is label the points and connect the dots so that the speed is never decreasing. So we've got 0, 30, 3, 37, 6, 45, 9, 54, and 12, 65. So something like that. I already set up the axes. And we're going to just kind of connect the dots. Doesn't matter if it's a straight line, but it can be never decreasing. So that's what our graph looks like. Next up, letter B, we're going to estimate the distance traveled by the car during the 12 seconds by finding the areas of 4 rectangles drawn at the heights of the left endpoints. This is called a left Riemann sum. All right, so I'm going to do this in green. We're doing the left endpoints this time. So this is a good introduction to integration because integration gives you the area under a curve, right? So what we're going to do is we're going to make different bars or rectangles on this graph with the left endpoint of the bar being a point that's on the curve. So it's going to look like this, where the left lines up with the curve and the right just goes straight across wherever it ends up. So it's going to look like that. These bars should all be the same width. You can see my 9 and 12 are a little bit close together, but that's okay. So let's try to calculate this. So we're going to estimate the distance traveled. Notice that distance would have normally a derivative of speed or a derivative of velocity. So now since we're doing integration, we started with the speed or the velocity. And if we find the area, it's taking us a step up to the distance. That's kind of showing you the opposite of derivative is integral. So we're going to estimate the distance traveled by the car during 12 seconds by finding the area of the 4 rectangles. Okay, so let's figure out this rectangle, right? If we find the area of a rectangle, it's the length times the width. So it's going to be 30 times 3. 3 times 30. The next one is going to also have a width of 3, so it'll be 3 times, and we said that was 37. The next one's going to have a height of 45. And the next one's going to have a height of 54. Notice that all comes from this chart, 30, 37, 45, 54, and that's the left endpoints of these bars. And if we multiply and add that together, we would get 498, and since this is a distance and our speed was in feet per second, our distance is just going to be in feet. So that's a pretty good approximation, and that's called a left Riemann sum. In part C, we're going to try to do a right Riemann sum. So we're going to estimate the distance traveled by finding the area of 4 rectangles drawn at the heights of the right endpoints. If we're going to want to get fancy here, this left Riemann sum, you can see that we're missing some pieces of the area. So this is going to be an under approximation of the actual distance traveled. But now let's try the right endpoints. So for this first bar, instead of going up to this height on the left, we're going to go up to this height on the right. And now I'm going to draw an orange. So there's our first bar. The second bar is going to go up to here. The next bar is going to go up to here. And the last bar is going to go up to here. Okay, so you can see now, hopefully when we calculate this, it's going to be larger because we're including all this extra space. And you can tell in the end it's going to be an over approximation because we're including these kind of triangular, almost shaped regions that are above the purple curve. So let's try this. So now we're going to have 3 times the right endpoint, which was the 37. And then 3 times 45. And then 3 times 54. And then 3 times 65. My pen is not doing great. It's dying a little bit, but we got it. And if you multiply and add those, you're going to get 603 feet, which is clearly larger than we got in letter B. And that makes sense, right? Based on our chart, it made sense that it was bigger. Okay, so now we're going to do one more time using a midpoint Riemann sum. And I'm going to go back to green, I think. I'm running out of colors. Actually, let's use this. It's like a magenta or something. So we're going to estimate the distance with 2 rectangles drawn at the heights of the midpoints. So if we're going to break this into 2 rectangles, they should be of equal width. So they're going to be kind of from 0 to 6 and from 6 to 12 along the x-axis. And we're going to the midpoint of the bar. So it's going to be right here, straight across. And this one will go to this midpoint. And even though these bars are bigger than the ones that we did before, this might actually be the best approximation yet because you can see these triangle looking regions are almost going to be able to cancel each other out. Now this isn't, a perfect sketch, but that is not bad. This is going to be pretty good, I think. So we only have to multiply 2 different rectangles this time. So the first one, now they have a width of 6. This first one has a height of whatever the 3 y value was, which was 37. And the other one has a height of 54, which was the y value for x equals 9. And this is going to give us a total of 546 feet, which is between the first 2, which makes sense because it's not really much of an over or under approximation. It's probably not perfect because this is an approximation, but it's pretty close. All right, so that's how you do a Riemann sum. Now let's try doing a Riemann sum with an actual function. Given the function y equals x squared plus 1, estimate the area bounded by the graph of the curve and the x-axis from x equals 0 to x equals 2 using a left Riemann sum with n equals 4 equal subintervals. All right, so let's see what we got. We're going to go from 0 to 2, and we're going to be doing 4 subintervals. So I'm going to split this into fourths. So we've got 0.5, 1, 1.5, and 2. and we're using x squared plus 1. So I'm going to try to sketch this graph here. I'm going to go, it's going to be going from 0, I'll plug in 0. Actually, you know what? I'm just going to make a chart so that we know for sure what all of our y values are. We're going to be going from 0 to 2, and it's important that we split this into fourths. So I'm going to put 0, 0.5, 1, 1.5, and 2. And if I plug each of these into the function, I'm going to get a y value of 1. 0.5 gives me 5/4. 1 will give me 2. 1.5 will give me 13/4. And 2 will give me 5. I know I switch between decimals and fractions, but either way works. So then we want to do a rough sketch of this here. And we have to go up to 5 on the y-axis. Got 1, 2, 3, 4, 5. And let's sketch this. So we have a point at 0, 1. We have a point at 0.5, 5/4. 1, 2. 1.5 is up at 13/4, so 4, 8, 12. That's a little bit bigger than 3. And then 2, 5. It's going to look something like this. Makes sense, it's increasing faster because it's a quadratic, so it would be like a parabola. And we want to do a left Riemann sum with 4 equal subintervals. So it's going to look something like this. And when it says equal subintervals, it means the width is going to be equal. So each one of these has a width of a half. And we can actually write that into our formula. Since each width is a half, we can pull that out in front. And then we can just add all of the left heights together. So it's going to be 1 plus 5/4 plus 2 plus 13/4. So think about that. If we distributed the 1/2, we would have 4 different rectangle area formulas. 1/2 times 1, 1/2 times 5/4, 1/2 times 2, 1/2 times 13/4. We could combine it to make it a little bit nicer to calculate, like this. And when we add and multiply this, we're going to get 3.75. So that's our left Riemann sum. All right, now we're going to do the exact same thing, but for a right Riemann sum. So we already have the chart, so that's kind of nice. And I'm going to do a rough sketch of this graph once again. And it looks something like this. Okay, and now we're going to be doing a right Riemann sum. So it has to go to the right endpoint of each box or each rectangle. Ooh, I definitely screwed up that width because those look different widths, but those should be all the same width. And let's see, this time we still have a width of 1/2 each time. And now we go based off of the right endpoints for the 4 different heights. So we're going to have 5/4, 2, 13/4, and 5. So we add all those together and multiply, and we're going to get 5.75. And just like in the question on the previous page, you can see that this is an overestimate. Our boxes are above the curve. So it makes sense that our answer is larger than in this one when we had an underestimate. There's portions of the curve that are still not included in our boxes. What about letter C? Now we're going to do a midpoint Riemann sum with n equals 4 equal subintervals. So once again, I'm going to quickly sketch this. Looks something like this. I feel like every time I get a little bit better. And now we're going to be trying to figure out what's the midpoint of each of these. What's the y value when the x is the midpoint between each interval? And so I'm going to try my best to do a good sketch of these bars. Okay. Not too bad. And this time, we're going to need some different numbers because, let's see, the midpoint between 0 and 0.5 is going to be 0.25. So I need new y values. I don't have the y value for 0.25 yet. The midpoint of this subinterval is going to be 0.75. The midpoint of this subinterval is going to be 1.25. And the midpoint from between 1.5 and 2 is going to be 1.75. All right, so I already took the liberty of plugging each of those x values into this original function, and I got the new y values. We got 17 sixteenths, 25 sixteenths, 41 sixteenths, and 65 sixteenths. So I'm going to start with those. And once again, each of our boxes, each of our rectangles has a width of 1/2. So I can start with 1/2, and now I'm just going to add all the heights together, which are these y values. So we're going to have 17 sixteenths plus 25 sixteenths plus 41 sixteenths plus 65 sixteenths. And when we add these together and multiply by half, we're going to end up with 4.625. And you can see that that number is between the other two approximations because it's not quite an under or overestimate. It's just pretty close estimate. I'm not sure exactly how close this is to real life, but it's pretty close, right? Okay, that brings us to the idea of a definite integral, which answers the question, how can we get the exact area under a curve? And to figure that out, you have to think about what if we could take these Riemann sums, and I think it's pretty clear that the more rectangles that we use, the closer our area would get, right? Like picture if our bars were really close together, and instead of having 4 bars, what if we had 20 bars, and each one had the width that was much smaller? Then this would be a better approximation. We'd be leaving out less. So what if we could have bars that's with areas so small that they had a width of close to 0? And if you do that, you're getting into our integrals. So that's going to be how we answer this question. How can we get the exact area under the curve? We're going to define area as the region bounded by the curve and x-axis. So it's going to be bounded by the curve on top and by the x-axis on the bottom between two numbers. So it's going to be between x equals a and x equals b. All right, so this is what our formula looks like, integral from a to b of f of x dx. And this limit notation is showing you what if we could take our number of bars in our Riemann sum and make it infinite, right? This is summation notation, which is going to come back a lot later in this school year. But from 1 to n, what if we can make infinite bars? What would our sum be? What would our area be? Okay, we're not going to get too much into that notation right now, but that's what the fancy pants notation looks like. Let's keep going. Properties of definite integrals. If we have a definite integral from a to a, so if it's starting and ending at the same place, it literally has a width of 0. It doesn't matter what the height would be. If a rectangle has a width of 0, 0 times any height would be 0. This area is 0. The integral would be 0. If we have an integral from b to a, and you want to switch it to be from a to b, the answer is a negative version of the original. And if we have some sort of a constant that's multiplied by a function within an integral, it's the same as if we pulled a constant out in front. like that. Okay, it is important to note that although if you're adding or subtracting two functions inside of an integral, you can separate them into separate integrals. You cannot do that with multiplication and division. So if we have f of x times g of x within an integral, it does not equal the integral of f of x times the integral of g of x. Same is true for division. All right, so in the next 4 questions, we are going to just practice figuring out an integral based off of geometric formula, so based off of the area that we can see on the graph. We're going to get into actual integral rules in a little bit, but let's try this. So start off here with letter A. We have a function y equals 4. So if we were going to sketch this, 1, 2, 3, 4, it would look like a horizontal line at 4. And we're trying to find the area under that curve between x equals 1 and x equals 6. That's what this means. So this is at 4. And so what we're going to do here is picture that from 1 to 6, we're trying to figure out what this area is that's bounded by the x-axis and this line. And to figure that out, we can just say, hey, wait a minute, this is a rectangle, right? So it has a width from 1 to 6 of 5 and a height from 1 to 6 of 4. So if we do 5 times 4, we'll get 20. And that's our area. Okay, so that's our integral. We can do the same thing in letter B. X plus 2 this time. We're going from 1 to 3, so I'm going to draw that down here. And let's make our y-axis. And if we're going for the function x plus 2, that's going to be a line, right? And it has a y-intercept of 2 and a slope of 1. So it's going to go up 1 over 1, up 1 over 1, up 1 over 1, and so on. And so we're interested specifically, though, from 1 to 3. So we want to know, what is this area? And to figure this out, we can think of this as a trapezoid. Trapezoid has an area formula of 1/2 times height times the sum of base 1 plus base 2. And if you've ever done a trapezoidal Riemann sum, then this formula is hopefully familiar to you, but let's fill this in. So this is actually kind of a sideways trapezoid, right? So the base 1 and base 2 are the parallel sides of a trapezoid. So the bottom and the top here are not parallel. The left and the right are parallel. So if we think about this sideways, the height is this sideways version, which would be like a vertical distance, which is a height of 2. And then we have base 1 and base 2. So if I plug in 1 here, the y value is 3. If I plug in 3 here, the y value is 5. So again, this is the height. This is base 1 and base 2 of this trapezoid. Well, this is really just like a fancy version of saying, what if we had a rectangle with height of 2 and width of 8? And then we chop it in half because the trapezoid is only half of that. But we don't need to get into all that. So if we figure this out, though, we're going to have 3 plus 5 is 8 times 2 is 16 divided by 2 is 8. So our area is 8. All right, let's get into a little bit more complicated one here in letter C. So now we're going to go from -2 to 2 of the square root of 4 minus x squared dx. Square root of 4 minus x squared is a semicircle. So if I go and plot this on a graphing calculator, what you'll see is it's actually semicircle like this. If I plug in anything bigger than 2 or smaller than -2 into this, it's going to be a non-real answer, so it doesn't even show up on the graph. So that is the entire graph, and we're trying to figure out the area from -2 to 2, so the whole thing. So if we think about this as a circle, we're going to be looking for half of the area of a circle, 1/2 of the pi r squared. And the radius of this circle, hopefully you can see, if this is the center point of the circle, it has a radius of 2 in every direction. So it's going to be 1/2 of pi times 2 squared. And so we have 4 times 1/2 is 2. So the answer here is 2 pi. That's our area. All right, last one. Over here, we're going to be going from -4 to 4 of this curve. Well, it's not a curve. It's a bunch of line segments. And now it's important to realize that if we have anything below the x-axis, it's a negative area. So I'm going to do anything below in red and anything above in green. So from -4, 1, 2, 3, 4. So we've got this whole section over here that we want to kind of get rid of. Then we've got this section right here that's positive. And then we've got this section over here. We're going to 4, 1, 2, 3, 4. So this section over here is negative. So let's see if we can figure out how to find the area of each of those. So the first piece is negative. It's a triangle, so it's going to be 1/2 base times height. And we have a 2 and a 3 as our base and our height. Then we have the positive triangle. This can all be thought of as one triangle here. And we have a base of 3 and a height of 3. And then we have another negative piece, and it's going to be 2 and 1. Okay? Got some like red and green, some holiday colors going on here. Well, let's combine these. So we're going to end up with -3 plus 9/2 minus 1, which is going to give us a total of 1/2. So even though there's a whole bunch of area going on over there, because a lot of it was negative, the total is only 1/2. Okay? So now we're going to use some of those properties of definite integrals from the top of the page. Again, those look like this. And we're going to apply those down here at the bottom. So given that the integral from 0 to 3 of some function is 4, and the integral from 3 to 7 of some function is -1, let's find these three integrals, the integral from 0 to 7. So for the integral from 0 to 7, we can split that up into the integral from 0 to 3 and the integral from 3 to 7. And the reason we would want to do that is because we know the integral from 0 to 3, we know the integral from 3 to 7, and combine these and you'll get this. That's a property of integrals. So now we're going to end up with 4 plus -1, or 3. Let's try letter B. So from 3 to 7, 2 times f of x dx is going to be, we can pull a 2 out in front. So it'll be 2 from 3 to 7 of f of x dx. And from 3 to 7, f of x is -1. So this becomes 2 times -1, or -2. And then in letter C, from 5 to 5, this is one of those trick questions. If the integral starts and ends at the same value, the answer is always 0. It doesn't matter what the function is. Boom. All right, so there's some properties of integrals for you in practice. Let's keep going. The next page has a ton of formulas for integrals, and they all come from the reverse of the derivatives. And we're going to apply a bunch of these. I'm not going to read through them. You can read through them on your own if you would like. We also have that sum and difference integral, where I already told you that you can separate these. We already know that we can pull a constant out in front, and we already talked about that multiplication and division don't work. So let's move into some practice questions. First up, we're just going to use kind of the reverse power rule, right? So whenever we are just taking a straight up integral, we want to add 1 to the power and then divide by the new power. So for 3x squared, we start with 3x. Instead of 2, we add 1, and then we divide by the new exponent. We're going to do the same thing here. add 1 to the exponent and divide by the new exponent. And if there's no x, we add an x and divide by the new exponent, which was just 1. And for every integral, for every indefinite integral when there are not bounds listed, we want to write plus c at the end, because we don't know what the constant might be, right? Whenever we take a derivative, the constant at the end drops off, right? The derivative of 4 is 0. It goes away. So if we're taking an integral and it doesn't have bounds listed, we don't know where the bound, like we don't know where this might be positioned on the graph. We know the shape of it, but it could be anywhere up or down. So the plus c accounts for that. We can talk more about that in class if you want. But I'm going to do one more step here just to kind of simplify this. So this is going to become x cubed minus 5 halves x squared plus 4x plus c. There is no product rule or quotient rule for antiderivatives, so sometimes you must simplify first. So I'm going to FOIL this, then take the integral. So if I FOIL, I'm going to get 2x squared plus 6 minus 1 is plus 5x, and then minus 3. And so we're going to end up with 2x cubed over 3 plus 5x squared over 2 minus 3x over 1 plus c. And then I'll rewrite that to 2/3 x cubed plus 5 halves x squared minus 3x plus c. For this next one, we also don't have a quotient rule, so we're going to simplify this first. So it becomes x to the 3 halves, because it's 2 minus a half, because x to the square root of x is x to the 1/2. And when I divide with the same base, that x, we subtract the exponent. So 2 minus a half will give us 3 halves, minus 2x to the 1/2, because it's 1 minus a half, plus 7x to the negative 1/2, because this 7 didn't have an x, so I do 0 minus a half, I get negative a half. And so let's do this integral. So we're going to end up with x to the 5 halves divided by 5 halves. So I'm going to divide by the 5 and multiply by the 2. Then we have minus 2x to the 3 halves divided by 3 multiplied by the 2 plus 7x to the positive 1/2 divided by 1 multiplied by the 2 plus c. So if I'm dividing by a fraction, I'd put the numerator on the bottom and the denominator on the top, right? That's how I'm kind of like flipping and multiplying. And I'm going to end up with a simplified version here, 2/5 x to the 5 halves minus 4/3 x to the 3 halves plus 14x to the 1/2 plus c. All right, so a little bit uglier, but that's a perfectly fair integral. All right, we got a few more examples to look at here, so let's keep going. Next example, a particle moves along the x-axis at a velocity of v of t equals 4t cubed minus 3t squared plus 5, for t is greater than or equal to 0. At time t equals 2, its position is x equals 3. Find the acceleration function. All right, so we've got the velocity. We can find the acceleration function by taking the derivative, right? Because it goes, the order goes position, velocity, acceleration. So if I have the velocity, the derivative would be the acceleration, the integral would be the position. We can always go up or down this chart using derivatives or integrals. So our a of t is going to be what? We got to remember back to our derivative rule, so it's going to be 12t squared minus 6t, and the 5 goes away. So there we go. If we wanted to find the position function, now we've got to move up. So we're going to take the integral. So the s of t is the integral of v of t. So we're going to take 4t cubed and add 1 to the exponent, divide by the new exponent. We'll take 3t squared, add 1 to the exponent, divide by the new exponent. 5, create a t, divide by the new exponent, which is 1, plus c. And this becomes t to the 4th minus t cubed plus 5t plus c. Don't forget the plus c. Now this actually can be taken one step further, because if you take a look up here, it told us a scenario for the position function. It said at time t equals 2, position is x equals 3. Now the question will tell us that to help us be able to figure out what c is. So we know that the position is 3 when t is 2. So I'm going to plug 2 in for t here. And by doing this, we have plugged in for s of t and for t, and we can find c. So if I actually calculate this out with everything to the other side, I'm going to get that c is negative 15. And you can try that on your own if you want. And so our final answer is going to be s of t equals t to the 4th minus t cubed plus 5t minus 15. If we take the derivative of this, we'll end up with the velocity. If we take the derivative of the velocity, we end up with the acceleration. Okay, next up, we have integration using u substitution. So when we differentiated composite functions, we used the chain rule. The reverse process is called u substitution. So for derivatives, we can use something called the chain rule. For integrals, we've got to use u substitution. So let's take a look at this first question here. The integral of x squared plus 1 to the 5th times 2x. Now normally, if we didn't have a process called u substitution, we would have to multiply all of this out in order to be able to take the integral. We'd have to kind of actually multiply x squared plus 1 by itself 5 times and then distribute 2x and then take the integral using our reverse power rule and everything. But we can change this if we say, let's let u equal x squared plus 1. And now if we take the derivative, and we're going to do that with these differentials, we're going to say du equals 2x dx. So you take u and it becomes du, and x squared plus 1 becomes 2x, right? The 1 goes away. And then we write dx at the end. And now, anytime that we see 2x dx, we can replace it with du. And anytime that we see x squared plus 1, we can replace it with u. So let's try that. We're going to end up with u to the 5th, as the x squared plus 1 was replaced. And then 2x dx becomes du. So suddenly this became a much simpler integral, right? Because now we can take the integral of that pretty simply. We increase the exponent by 1 and divide by the new exponent. And then we write plus c at the end. And the last step is going to be to replug in the x version. So we know that u is actually x squared plus 1. So this is really x squared plus 1 to the 6th over 6th plus c. We don't know what c is. We weren't given an initial condition in the question. But we were able to do this pretty simply without trying to multiply all that together. So that was nice. The question, though, is how do we know what to make u? And usually what I want to look for when I'm determining what u is going to be is I'm going to try to see, can I find like a composite function where there's a function inside of another function? Here I have x squared plus 1 inside of something to the 5th power. And the best case scenario is going to be if I can find that function inside of another function and that function's derivative is also in the integral. So x squared plus 1 has derivative of 2x. I'm going to think that through in my head. And I know the 2x is also here. So that's really good. That's really good. Okay, so let's try that strategy here in the next one. I see we have something to the 4th power. Do I have the derivative of 2x cubed plus 5? That derivative would be 6x squared. I have the x squared, and a constant like a 6, a coefficient like a 6, is not going to be that big of a deal. We're going to be able to handle that. So let's do it. So we're going to say, let's let u equal 2x cubed plus 5. So our du is going to be 6x squared dx. So we don't quite have all of this in our function yet. So let's see if we can rearrange our function so that it looks like this. So we're going to have an integral. The 2x cubed plus 5 is just perfect. It's just sitting there waiting for us. This x squared piece is a little bit different. So all I did was switch the order of the two multiplication objects that were in our original expression. We're allowed to switch multiplication around, we know that. But I wanted it to be 6x squared, not just x squared. So what I'm going to do is I'm going to add in a 6 here and then put a 1/6 in front of the integral. And I did that so that this will show up over here, and this already showed up. And that way I can get rid of every trace of x that ever existed in this question. So now I have 1/6 the integral of the u to the 4th times du, right? This whole thing just becomes du. And now that's a key piece of our new integral. Now we're integrating in terms of u, and we've got u to the 4th. So we can definitely do this. So we have 1/6 times u to the 5th over 5 plus c. And let's see. I'm going to combine this so it's over 30. And then we can plug the u back in. So it'll be 2x cubed plus 5 to the 5th power over 30 plus c. And I just thought while I was writing that, the integral was all multiplied by 1/6. So you might have a question, why am I not multiplying the 1/6 also times the c? Remember, the c is just a constant. It can represent any number. So it doesn't matter if it's multiplied by 1/6. That doesn't change the final answer because we still don't know what c is. And multiplying it by any other constant is still going to make it any number. So we don't even have to write that it's multiplied by 1/6. You can still just write plus c. All right, let's try one more of these. Integral of x times the square root of x squared plus 3 dx. This time, hopefully you can see that there's an x squared plus 3 hiding inside of our square root. And if I take the derivative, I'm going to get 2x. And that's good news because I already have an x. So I'm going to rewrite this so that I have a 2x dx at the end. So I'm going to have the integral of the square root of x squared plus 3 times x dx. I need to have a 2 in there. So I'm going to write in a 2 and a 1/2 so that they cancel out technically. And now I can rewrite this as 1/2 times the integral of the square root of u times du. And I'm going to rewrite this again with the square root as a power so that it's easier to take the integral. So we have 1/2 times u to the 3 halves divided by 3 multiplied by 2. And the 2's cancel out, which is awesome news. So we end up with u to the 3 halves over 3 plus c, which when I replug in my x squared plus 3, I'm going to get x squared plus 3 to the 3 halves over 3 plus c. Boom. There we go. Now we are pros. Okay, we've got 5 more u substitution questions to try. Okay, so let's try this. So for this first one here, actually, you know what I'm going to do here? I feel like it's going to take me a lot of time to write all of these out. I already have my answer key here, so I'd like you to try these questions, but I'm just going to quickly walk through them to show you what to do each time, so you don't have to watch me hand write everything. But if you want to try these on your own, go ahead and look at the PDF to see the questions, and then you can try them and then come back and check your work. I'm just going to walk through the steps here for each one of these. So first off, in this first one, given the question, we're going to let u equal 3x squared plus 4, and du it becomes 6x dx. In order to be able to plug this in, we needed a 1/6. And then once we switch this to u to the negative 1/2, we integrate, it becomes 2u to the 1/2, and then we plug the u back in. In the second question here, now we have trig functions, so we can let u equal what's inside of the cosine, which is 3x, so du becomes 3 dx. When we plug this in here, the 3x becomes a u, and in order to plug in du, we needed a 1/3, so that the 3 dx can be changed to du. We integrate, so cosine integrates to sine, right? Because the derivative of sine is cosine, so the integral of cosine is sine. It's Santa Claus, negative Santa, negative Claus. And then we plug back in the 3x. All right, we can do the same thing in the next question. Since the sine x is the one that's cubed, that's going to be our u, is going to be the sine x. Lucky for us, the derivative is cosine x. So that means that when we plug this in here, cosine x dx becomes du. The sine x is what's cubed, so the u is now cubed. And we integrate and then plug back in sine. In the next one, we can do the same thing, except this time we are going to let u be sine of 5x, because that's what's cubed. The derivative of sine 5x is cosine 5x times 5. So that's good news because we have a cosine of 5x. The 5 is our coefficient, or our number in front here, so we're going to have to multiply by 1/5 in order to be able to plug in du. And the sine of 5x, which was cubed, becomes u cubed. We integrate and plug that sine of 5x back in. And very similar in the next question, but it's a little bit more complicated. The cosine of x squared is what's raised to the 4th power. So I'm going to let u be cosine of x squared. The derivative is negative sine of x squared times the derivative of the inside, which is 2x. So now we have kind of a chain rule in this derivative, but it's part of our u substitution for our integral. It's a little bit more complicated, but let's check this. So sine of x squared is right here. The 2x, we had an x. So we still need a 2 and a negative. So that's why this negative 1/2 came into play in front of the integral here. And then everything else just turns into u to the 4th or cancels out and becomes part of the du. We actually do the integration, and then we plug the cosine of x squared back in. All right, so that's how those 5 questions go. I know I kind of blew through those pretty quick, but let me know if you have questions. And good luck with the worksheet, with the practice problems. And I look forward to hearing how you did. All right, thanks. Have a great day.